Um, so I actually almost never been, I mean, maybe never been into the algebraic geometry or algebraic geometry seminar, but today I went into the chairman job. And yeah, let me introduce my collaborator, Kentaro with Kobe University. And today he's going to talk about deformation of reaction to Z or Z mod reactions on the surfaces. And Julia for sharing. So maybe after the seminar again. Yeah, one.
Seminar. Thank you for your introduction and inviting me this opportunity. So alpha p action, GP actions on surfaces, two-dimensional case. Actually, so we started this field of studies with Hiroyuki Ito. His teacher, it was, so his mentor was Miyanishi, and he gave a series of lectures in Taiwan University about 30 years ago. And yeah, it's related. And yeah, nowadays these topics are, especially this topic is very hot and studied by many other mathematicians. I will explain later. And yeah, so Nobuo also study this topic, but mainly higher dimensional case, maybe, and the two-dimensional case are little. So we start with algebraic of characteristic P. We always assume it is. And so we consider group scheme of local type. This can be written as and this is a Hopper algebra with multiplication case. And this is addition. And this is a group scheme. Yeah, only existing positive characteristics. Okay. This is actually the kernel of this multiplication of GA. Yes. We consider action of a certain K group scheme. Let me call phi. And this action, the scheme theoretic action, corresponds to the action of Hopper algebra. Where we consider the case, special case, local surface setting, local two-dimensional. It's Y. And this action is given of this base field. Then the coaction on the in a very explicit way. So we take an element F, then this maps to I. And this delta I is a delta IF is a coefficient of T power to I, and I is K linear endomorphism. This and satisfy certain conditions the condition comes from this action, action. So I should write here g x g x convex, and this given by multiplication of this group scheme and identity x. And this is action and identity of z, and phi action and action. And one more condition. Sure. Identity element of G and identity of X. Action. Then this is identity of X. So these two conditions give the following restriction condition on delta I. Delta I should satisfy these conditions. If delta I should equal to can be written by delta 1. Here I is 0 to p minus 1, and delta 0 is identity. Delta 0 is identity. So the delta 0 is identity. Delta 1, delta 1, delta 1, delta 1, 0 is identity. Yeah, the same thing. So the important, only the important operator is delta 1. Thus, determined by delta 1, and delta 1 should satisfy Leibniz rule. So this delta 1 is a derivation. And since this action is given by alpha p, this derivation should satisfy also condition of additiveness. We'll explain. We define this notion in a more general case. We take a derivation over K. Then delta is called additive. If delta to P is 0, and also P close there exists rational function. This is a fractional field. Of our ring, and this satisfies delta E is equal to A delta. So additive one is actually P closed, and P closed derivation is important in the context of Galois theory, inseparable Galois theory, by Jacobson. He gave a purely inseparable Galois theory many years ago. Purely inseparable Galois theory. This describes inseparable extension in terms of p-closed derivation. And later, his theory is extended in very general case. So any field extension of finite, and it's now called Jacobson-Bourbaki theorem. And maybe, so algebraic geometers, maybe, so maybe for some, maybe representation theorists, maybe know a PD group and it's also created P group, but algebraic geometry maybe like more with Rudakov-Shaparevich solution. They started K3 surfaces, vector fields, K3 surfaces. Actually, they showed non-existence of regular vector fields on K3 surface in characteristic case by means of p-closed derivations, but without mentioning Jacobson's work. Anyway, and quotient by derivation of surfaces, the more general, so field, so higher dimensional case also, more general setting, and also one show Archin's work. By in a positive characteristic case, yeah, in this case, the quotient is Galois, so separable case, but it's very difficult to describe it. But except in this exception characteristic, if this is characteristic to singularity, we written very explicitly. It's very so if P is greater than 2, in this case, it's very difficult. Not the invariant ring is not obtained explicitly in an explicit way. And a little later, Artin studied in positive characteristic case. So he rational double point and found that there exists a non-total rational singularity. So the Dynkin diagram, ADE Dynkin diagram cannot determine the analytic isomorphism class in positive characteristic case. It's different from characteristic zero case. So later, the Peskin and more recently, Schreier and Lorenzini and many others studied these quotient singularities, mainly Z over P quotient singularities. Miyanishi and Ito published a textbook on these singularities. Miyanishi and Hiroki Ito algebraic surfaces in positive characteristics. This is a textbook, and there are many examples and explains on RDP and other things, many interesting stuff. So it is a fundamental difference of this kind of studies. And I also study quotient singularity, quotient surface singularity given by Z over P action. I actually studied quotient singularity by Z over P action. This action is a diagonal action on a product of two curves, and I give an explicit desingularization of this kind of singularities and solved some problems by Schreier, Ito, and Lorenzini. So the main difference is the following. In the characteristic zero case, the dual graph of cyclic quotient singularity is like this. This is a dual graph of the desingularization of surface singularity, and this is a chain of P1, and this is a dual graph. In the positive characteristic case, this is a like this. And one example, there are many these kind of and self-intersection number of these components, and I give an intersection matrix, and then I give many formulas to calculate invariance associated to this kind of quotient singularity. In this case, there exists only one node. Node is a vertex with more than 3 edges. Yes. This node, the number of node is usually 1, but in general, this can be this cannot be 1 in general case. And this is a very difficult problem. And in that case, there is no way to calculate the invariance at this moment, compute this kind of invariance at this moment. But I think if we establish the deformation theory of singularities, then we can calculate this kind of very difficult. We can do this kind of very difficult singularities in the same way as in singularity with only one node. So the deformation may be interesting problem. But I want to know some recent work. Some of them are only preprints, but available. 松本。2021 2000、2021 and 2020, 2022. He refined the result of Argin, yeah, very recently. Do not mention details, but yeah, interesting paper. Yeah, two more interesting papers. Read okay. And and Matsumoto. Yeah. They study RDP singularities recently. And so their results can be applied to studies on K3 surfaces. But I had not explained. Yeah. So these are explanation of history of quotient singularities in positive characteristics. Let R be K algebra. I will explain the deformation of on surfaces. Take a element, non-zero divisor, and non-unit. The typical example is the following. Double square bracket lambda, formal power series ring with one parameter lambda. And AP formal power series with two parameters. This is a deformation of two-dimensional disk over spectrum of R. The coordinate ring is given by we will consider deformation of derivation. And this is a little generalization of derivation is called quasi-derivation. Plus it has additional terms. This is called quasi-derivation. One more condition, additiveness. So, two conditions. Then this corresponds to automorphism of order P of A, the ring A, the R algebra A. This function is explicitly given by the following formula. This action will C A lambda on A spec spectrum of A. Here is lambda is group scheme. Divided by TP. マイナス1がマイナス1です。And addition, the form multiplication is given by just same as alpha p. It is a finite subgroup scheme of GA all GA over R. And the alpha p and ZP at the same time. If we localization over R localized by lambda is Z over P Z. And specialization by the ideal generated by lambda, then we obtain alpha p. So this is of alpha p to ZP. This is a total space. So this is a little abstract, so I will give a very explicit example in positive case. And also this is RDP and DK. P for one singularity is given by the equation plus y plus xy square equals y. And this singularity can be constructed by quotient of these action. Very simple. Easiest non-trivial action, I think. In the algebraic geometry, the quotient scheme is given by invariant ring, spectrum of invariant ring. In this case, the invariant ring is just norm, two norms, one more element. If we call these elements a small xy, then isomorphic to P for one singularity. And then, so I want to give explicit example of pseudo derivation. Yeah, in this case. Yeah. To this end, I will describe sigma of identity plus pseudo derivation. So, maybe. Okay. Sigma is equal to identity plus delta. That is pseudo derivation. So this the following qualities. In the characteristic two case, the condition is really simple. And this is additive. So delta square is equal to 0. Two cases, there exists one more. So D4 is auto singularity. So D4 is the linking diagram is like this. And there exists one more singularity with this linking diagram. And the equation is given by this. And these two singularities are not isomorphic, analytically isomorphic. In this case, this singularity cannot be given by G2 action, but this singularity can be obtained by alpha quotient of alpha 2 action. And as I mentioned before, correspond to derivation, and derivation is x square dx plus this is partial derivation, and dy. I usually use this notation. In case, the quotient singularity is also given by invariant ring, and in this case, invariant ring is given by kernel of this derivation, and this kernel has a very simple this is isomorphic. Okay. We want to connect these two singularities by means of G lambda, the group scheme G lambda over R. So we recall the derivation, the type of derivation. In this case, derivation is given by two conditions. And in the first case, so these action, in the case of this action, the pseudo derivation is given by two conditions, two equations. So they are very similar, and we can connect these two pseudo derivations by adding lambda here and here. There does not exist a general strategy, but in this case, we can connect these two actions by adding two lambdas. And we can solve this equation. So we luckily obtain the deformation of the connect two kinds of singularities with same thinking diagram. This also works for E6 singularity in characteristic 3. I want to explain one more example. In this, to this end, I will consider one-dimensional case, one action and the lift of one-dimensional action first. So by the Artin-Schreier theory, we know Z on K the double bracket X, so formal power C, this ring can be defined by conductor. And this action actually action on the fractional field. And after replacing this uniformizer X, right, by the Artin-Schreier theory, we can write the action this way. E is this group, this gives a constant group scheme. This corresponds to constant group scheme given by E. And here I use this T. So usually we write it 141. And this conductor satisfies two conditions. Alpha is not divisible by P and P is possible. So using this description, nice description, I want to degenerate this action by means of quasi derivation. So we consider action of G on this formal power series ring. So we have this equality, and we want to put some lambda inside this correspondence, this map. Lambda is hidden in this correspondence. So if we put if we let lambda be 1, so the action should satisfy this correspondence. So this should satisfy. After observations, we obtain degeneration of GP action to alpha P action. As a point. We use this minus x. Then lambda. Delta lambda is a desired one. So this is if lambda is equal to 1, this is the original. This gives the original action of ZP. And if we let lambda be 0, then we obtain derivation. So alpha P action. More explicit can be written. So if the action is a diagonal action, then we can lift alpha P action to GP action in this way, in the even in a two-dimensional case. But there exist many important cases that where the action does not split. For example, characteristic 2 cases, E6 singularity is given by no split action. Yeah, it's 0 singularity. E6 1 singularity. And this singularity is so alpha P quotient singularity and alpha 3 quotient singularity, and the corresponding derivation is y3bz, maybe x, but yeah, it's useful. Explicit calculation. So this z is related to z, so I use z instead of x. So in this case, here this is dz, but z is in this term, and y dy here, and y square y so cube exists in the coefficient of dz. So this is different from D4 case. In that case, the action splits two axes. In that case, we can use one measure deformation, result on deformation. But unfortunately, we can lift this type of derivation. This is one of that with Ito, study with Ito. So here, F0 and Z or I0 is given by a certain formal power series with variables x, p, and yp, and g, I0, yeah, sorry, I equals, and this the formal power series with two variables xp and yp. P minus 2. In this case, this action is liftable. Explicitly, there exists delta lambda with this delta 0, and we can calculate explicitly this delta lambda in that case. So this E60 can be connected by this result. Yeah, we can check it explicitly. Generic fiber, yes, generic fiber.
Are you saying that there are many ways to visualize these ones?
Many,
Depending on your F0 and GI.
I think so. Actually, so yeah, we have lambda and so if I remember correctly, in that case, the deformation is very in this case, maybe the deformation is rigid, but in general, it's not rigid. Well, yes. So the ambiguity is not clear. If we put some conditions, natural condition, then there exists only one lifting. But I'm not sure there exists only one lifting of E60. But maybe the yes, maybe you are right. We have to put some conditions if we want to obtain a special type of lifting. Yeah. And we put some mild condition, then there exists only one lifting isomorphic to E61. Is it an answer your question? Is it okay?
Or it's delta 0 if you were deformation of E60 or
E60.
also delta 0 if you deformation of E60. Is it yeah, do I understand correctly or
so you so we start with this singularity, then as a reduction, so sorry, reduction. So is it only unique reduction? Is it your question?
so this is when you said lambda is on 0 when you and delta 0 is yeah. What is the role of delta 0?
This case, so delta 0 is this one. Here, so the special case. So this F0 is y cube, and this is equal to y x. In this special case, this is dx. And this is x, y. In that case, we can apply this liftability to obtain deformation of this delta, specialty delta zero. This is a general case. So, sorry, it's not clear. So we have this theory, result on lifting. So if we consider this, if zero is equal to y q, and this so only one term x, only one term. So this is in general many terms, but if we put this side, this term x dy, then this gives delta zero. So this is liftable. So if we, of course, if we replace many other delta zero, and then we obtain many other singularities, it's not always not RDP type. There are many other singularities. So many other singularities can be liftable, can be lifted. Yes. But many still there exist many restrictions. So in general, delta zero can be written as f(p)x plus g dy, and fg is contained in kxy. So this is a general description of delta k xy. The delta zero should satisfy additivity. We start with alpha p action, so we put this condition. Then the question is there any lift? So for any delta zero of this kind, is liftable or not? And I do not answer. So we expect it is true and always liftable. But we don't know. This special case, we can lift. And this class of derivations contains E6 zero type derivation. Maybe this is a kind of problem of differential equation in positive characteristic, but it's very difficult to solve in general. We want to solve this kind of differential equation. So I want to mention some conjectures related to this problem. So liftability, additive. So alpha p is one of the conjecture for any additive equation. Then so if maybe this, but we do not have a good reason for any additive derivation. Lifting of this delta. The next one is related. by this condition, kind of integrability is derivation, but not sure. In that case, we should have this equality. So this gives a very efficient criterion for P closedness because so left hand side is equal to 0 if and only if delta is P closed. And the right hand side is very easy to calculate, but P closedness is very difficult. So we have to calculate these derivations, and it's very hard. We use computer, but it's very difficult and very easy to calculate. And so if we know some special cases, if so this is true for P is 2, 3, 5, 7, for example, and okay. And for example, this dxf is equal to 0 and dy is equal to 0. It's okay. And yeah, many other cases we verified this conjecture. For example, if delta is P closed, then this conjecture holds. So right hand side is equal to 0. But no, the other side, if this is equal to 0, then this is delta is P closed. It's important case. The inverse is important. There exist several conjectures, but I want to give one example. Maybe these two are most important conjectures in this context. And I want to give a proposition, but yes, it's a little complicated, so I just give x plus x power to m dy. M is positive. Delta P equals 0. It's if and only if m is equal to 2, then in this way, so the effectiveness depends on m, and so Tm we have a criterion of congruence relations. The exactly half of prime satisfies this condition. So, by the, なんだ、prime number theorem for, arithmetic progression. Yes. Yeah, in this sense, half of prime, we fix the number m, then half of the prime numbers, satisfies additiveness of the delta. Yes. Yes, we give this proof, but I think this only happens, only happens when these are monomials. But it's simple and beautiful result, I think. Yeah. So if m is more and more, so if m is bigger, then the condition is more complicated, but we can determine the condition for each m. Yeah, in general case, it's a little complicated, but we can determine this congruence condition. So this is almost a time. So thank you.
Thank you very much for the last talk. So any questions and comments?
So instead of alpha p, can you also consider mu p for the
Mu p, yes.
Yeah.
Yes. Mu p, yes, I consider. Mu p also have a deduction to alpha p, not zp. So the deformation space like this. So alpha p here and zp and mu p. And today we consider this deformation. Yes. Yeah, we can ask deformation also. Yes. I'm not sure, but I think mu p is a little easier because the action may be a little rigid. So the quotient singularity is almost always toric. If the action fixes non-Cartier Bayes divisor, in that case, maybe it's a little easier, but yeah, we don't know the exact answer to your question. Yeah, we should check it. マジ本当
データじゃないけど。
右辺が出る。
簡単なデータ。
出るじゃなかったら何あ、ほんまや。ソーリー。ソーリー。It's difficult. Sorry. dx by d.
Any other questions? There's no other questions. Let's thank the speaker again.
Next Friday, jump to the bigger talk. Yeah. So the next Friday, about 3:30 to 5. Thank you very much.